Welcome. Now we enter winter and reckoning, the beginning of episode 2 in our AI documentary. We've seen early optimism, groundbreaking firsts, and even programs that mimicked conversation. But now we reach a colder time in AI's history, when expectations exceeded reality, funding dried up, and the field itself was forced to confront hard questions. This is the story of the AI winter, a period not of failure, but of forced reflection. All revolutions burn bright at the start. There is excitement, there is ambition, there is belief. But what happens when the promises are not kept? When reality pushes back? In the 1970s and 80s, the field of artificial intelligence entered a season of silence. A time of skepticism, stalled progress, and lost faith. This was the AI winter. By the early 1970s, optimism in AI was running high. Researchers had built systems that could prove theorems, solve puzzles, and carry on basic conversations. DARPA, the U.S. Defense Advanced Research Projects Agency, poured millions into AI projects. Governments around the world followed. AI would revolutionize medicine. AI would transform the military. AI would run factories, plan battles, diagnose disease. It was only a matter of time, or so it seemed. But beneath the surface, cracks were forming, because many of these systems only worked in highly controlled environments, and the real world is rarely controlled. Most AI at the time was symbolic, rule-based, logic-driven, human-programmed. This worked well for small domains. But real-world knowledge is vast, ambiguous, and ever-changing. For example, how do you write rules for every possible medical case? How do you encode common sense? How do you teach a system that dogs have 4 legs, but still recognize a dog if it has 3? Even simple language posed challenges. The trophy didn't fit in the suitcase because it was too big. What was too big? The trophy or the suitcase? Humans resolved this instantly. Symbolic AI systems struggled. The gap between what AI could do and what people expected it to do grew wider, and patience began to run thin. In the UK, a major turning point came in 1973 when mathematician Sir James Lighthill published a report to Parliament on the state of AI research. It was damning. Lighthill argued that AI had overpromised and under-delivered. He claimed the field lacked measurable progress and had failed to produce useful, real-world applications. His conclusion? Much of AI research was not worth funding. As a result, the UK government cut funding dramatically, particularly for university research. The Lighthill report sent shockwaves through the AI community, not just in Britain, but worldwide. It marked the first official public loss of confidence in AI. In the United States, DARPA had invested heavily in ambitious projects, including machine translation and speech recognition. But the results were far below expectations. Translation systems failed to grasp nuance or context. Speech recognition systems required slow, clearly articulated speech, often in isolated words. In one famous failure, a system designed to translate Russian into English mistranslated "the spirit is willing, but the flesh is weak" as "the vodka is good, but the meat is rotten." DARPA began to pull back. Funding dried up. AI labs faced layoffs and closures. The first AI winter had begun. In the late 1970s, AI got a second wind, this time through expert systems. These were programs designed to replicate the decision-making of human experts, particularly in narrow domains. One of the most successful was MYCIN, developed at Stanford. MYCIN could diagnose bacterial infections and recommend treatments based on a series of questions and rules. It performed comparably to real doctors in its narrow field. And it marked a shift from general AI to narrow AI. Companies and governments poured money into expert systems. Entire industries were promised automation and intelligence. By the mid-1980s, AI was booming again. The winter was over. Or so it seemed. But expert systems had their limits, too. They were expensive to maintain. They couldn't learn. Every rule had to be added manually. They were brittle. One unexpected input could break the system. They didn't scale well. As expectations rose once more, so did disappointment. Systems that worked in labs failed in business settings. Maintenance costs soared. And by the late 1980s, the bubble burst again. The second AI winter began. Meanwhile, Japan had launched the Fifth Generation Computer Systems Project, FGCS, in 1982, a bold government-funded initiative to leapfrog Western computing. Their goal was to build machines that could understand natural language, perform logic inference, handle expert knowledge. It was backed by over $1 billion with support from top Japanese companies and universities. Western nations responded with their own initiatives, notably the US Strategic Computing Initiative and the UK's ALVE program. But by the early 1990s, Japan's project had failed to deliver. The hardware underperformed, the software lacked flexibility, and once again, the promise of intelligent machines faded into mist. The AI winters were not caused by a lack of progress. They were caused by a mismatch between expectation and reality. AI was, and is, hard, and early researchers often overstated what was possible. Some key factors. Over-promising. Visions of general intelligence and human-like machines by the year 2000. Limited hardware. Early machines were slow, memory-poor, and expensive. Fragile systems. Early AI systems could not adapt, learn, or generalize. Lack of data. AI thrives on data, which was hard to collect and process in the 70s and 80s. Shifting funding priorities. Governments and companies followed hype, then pulled back when results lagged. AI did not fail, but its context wasn't ready. The winters forced the field to mature. Hype gave way to caution. Theory was grounded in practice. The focus shifted from strong AI to weak AI, from human-level minds to practical tools. Researchers began to explore probabilistic reasoning, statistical learning, and eventually neural networks, a technology that had once been sidelined. In a strange twist, the winters planted the seeds of AI's rebirth, quietly beneath the snow. New ideas were germinating. Even during the darkest times, research never stopped. Some of the most important foundational work in computer vision, machine learning, natural language processing, cognitive modeling was done in the 1980s and 90s. Much of it was obscure at the time, published in niche conferences, supported by tiny grants. But these researchers believed in the long game. The true intelligence could not be rushed, and that winter, though cold, would not last forever. In every field of science, there are winters, times when the vision outruns the tools, when belief fades. But AI is a field born not just of logic, but of patience. And beneath the frost of the 1980s, new paradigms were forming, new architectures, new learning models, new ways of thinking. The mind would return, but not as logic, not as rules. It would return as connection. Let's move now to learning from the brain, where the cold logic of symbols gives way to something more organic, a return to biology, inspiration from neurons, and the long, winding road of neural networks. Here we trace their roots, their rejection, and their astonishing revival. This is not just about technology. It is about faith, persistence, and the rediscovery of an idea that would change AI forever. In the icy shadow of the AI winters, one idea refused to die. It was not based on logic, not on rules, but on the architecture of the mind itself. It imagined a future where machines didn't think like philosophers, but like animals, where intelligence wasn't a system of steps, but a web of connections. This is the story of the neural network. and how, after decades of exile, it came back to rewrite the world. Long before computers could talk or play games, scientists asked a simple question: what makes the brain intelligent? The brain they knew wasn't a rule-based engine. It didn't run on logic gates or symbolic propositions. It ran on neurons, billions of them, connected in vast, shifting webs, sending tiny electrical pulses. In the 1940s, two researchers, Warren McCulloch and Walter Pitts, proposed a revolutionary model: that neurons could be modeled using mathematics. They created the first artificial neuron, a simple system that could take inputs, apply weights, sum them, and produce an output. It was crude, but it laid the foundation for connectionism, the idea that intelligence emerges not from logic, but from patterns of activation. In 1958, a psychologist named Frank Rosenblatt built on McCulloch and Pitt's work to create a new model, the perceptron. This was a machine, an actual physical device, that learned to classify input patterns by adjusting weights between its artificial neurons. It could recognize simple shapes, distinguish letters, learn basic rules through trial and error. It was a learning machine, decades before machine learning became a buzzword, and the media took notice. Newspapers declared that the perceptron could walk, talk, and think. The Pentagon invested heavily in its development. It seemed miraculous, until it wasn't. In 1969, two researchers, Marvin Minsky and Seymour Papert, published a book titled Perceptrons. It was a devastating critique. They showed that perceptrons, as they were then designed, could not solve even basic problems like the XOR function, a logic gate that required combining multiple layers of decision-making. Their conclusion? Single-layer perceptrons were fundamentally limited, and at the time, multi-layer perceptrons, what we now call deep neural networks, were not well understood or easy to train. Funding dried up. Neural networks were declared a dead end, and for over a decade, connectionist models were pushed to the margins. The field returned to symbols and logic. The brain-based dream was frozen. But not everyone gave up. A small group of researchers, often ignored, sometimes ridiculed, kept the torch alive. They believed in learning by connection. In 1986, a major breakthrough arrived. Three researchers, David Rumelhart, Jeffrey Hinton, and Ronald Williams, published a paper introducing a training method called backpropagation. This algorithm allowed multi-layer neural networks to learn by adjusting internal weights based on errors in output. Backpropagation was the missing piece. It let neural networks self-correct, propagating errors backward through layers, refining themselves step by step. This changed everything. Suddenly, deep learning, once dismissed, had a roadmap. And in the 1990s, connectionism began to return. Slowly, quietly, but powerfully. This return sparked a debate that still echoes today. Symbolic AI. Precise, interpretable, explainable, but brittle and hand-coded. Connectionist AI. Flexible, robust, adaptive, but opaque, often a black box. Symbolic AI mimics reason. Neural networks mimic intuition. One is a map, the other is a forest. In practice, neural networks began to outperform symbolic systems in key tasks: speech recognition, handwriting recognition, basic vision tasks. These weren't glamorous breakthroughs, but they were real-world wins, and industry began to take notice. By the early 2000s, two forces emerged that changed everything. Big data. The internet had created oceans of information, images, audio, text, more than any team of researchers could label by hand. Faster hardware. GPUs, originally built for graphics, were perfect for training neural networks, performing thousands of parallel operations. Suddenly, deep networks could be trained at scale. What once took weeks, now took hours. And with more layers, more data, and more power, neural nets began doing things that no symbolic system ever could. In 2012, a team led by Jeffrey Hinton, Alex Krzyzewski, and Ilya Sutskever entered a computer vision competition called ImageNet. Their model, a deep convolutional neural network called AlexNet, crushed the competition. It reduced the error rate by nearly half. This was not an incremental improvement, it was a quantum leap, and it proved what deep learning could do. Within months, the entire field of AI began to shift. Google, Facebook, Microsoft, Baidu, Amazon, they all pivoted to deep learning. Neural networks, once laughed out of the room, were now the crown jewel. By the late 2010s, neural networks were everywhere. They powered speech assistants like Siri and Alexa, recommendation engines on YouTube, Netflix, and TikTok, image recognition for self-driving cars, language models that could translate, summarize, and even generate prose. And with the arrival of transformers and attention mechanisms, language modeling exploded. But that's a story for the next chapter. For now, the neural network had returned, not as a toy, not as a theory, but as the beating heart of modern AI. It was discarded, dismissed, defunded, and still, it endured. The neural network is not just an algorithm, it is a belief that intelligence is not coded line by line, but emerges from layers, from patterns, from data. It does not prove theorems, it feels its way through the world, and in doing so, it sees. We now stand on the brink of the modern era, with deep learning in full bloom and new models changing how machines see, hear, and speak. Let's continue with the minds that speak, where artificial intelligence finally begins to grasp something astonishing: the structure of language itself. Now, we explore how breakthroughs in neural networks gave rise to transformers, how machines learned to predict words, and how this quietly evolved into the most profound leap in AI since the field's birth. This is the story of language models, not just tools for translating or answering questions, but systems that begin to imitate something closer to thinking. Words are how we understand one another. They carry thought, emotion, memory, layer upon layer of human experience. But for decades, machines could only process language in fragments. Words were numbers, sentences were rules, understanding was an illusion. Until something changed. In the early 21st century, artificial intelligence found a new key. A way not just to process language, but to model it. Not just to respond, but to speak. Before deep learning, natural language processing, NLP, relied on hand-coded rules and shallow statistical models. Systems would tokenize sentences, parse grammar trees, match keywords to known templates. This worked for simple tasks, like spotting spam or extracting names. But for open-ended conversation, it failed. Language is ambiguous, contextual, creative. Rule-based NLP couldn't keep up. Then, neural networks entered the scene, first for translation, then for sentiment analysis. They used word embeddings like word-to-vec and glove, which allowed computers to understand that king and queen are related, or that Paris and France share a spatial similarity. But something was still missing: context. Word embeddings were static. The word bank meant the same thing whether you were talking about rivers or money. Real language requires dynamism. And so, the transformer was born. In 2017, a team at Google published a paper titled "Attention is All You Need." It introduced a new architecture, the transformer. It was unlike anything before it. Here's what made it revolutionary: attention mechanism. The transformer could look at every word in a sentence at once and assign importance weights to all other words. This let it focus on relevant context. For example, knowing that he in a sentence referred to John, not the dog. No recurrent loops. Earlier models processed words sequentially. Transformers processed entire sequences in parallel, making training much faster. Scalability. Transformers could be stacked and trained on massive datasets, millions, then billions of words. With this architecture, language models didn't just memorize word relationships, they began to learn how language works. The first major implementation was BERT, a model that could understand language in both directions, left and right. It didn't just finish your sentence, it understood how your sentence was structured. While BERT was built for understanding, another family of models would soon emerge for generation. The ability to speak rather than just interpret. The most famous? GPT, or Generative Pre-trained Transformer. Its approach was simple but powerful. Feed it a massive data set of text. Ask it to predict the next word, then the next, then the next. This next word prediction game turned out to be more than a toy. It allowed the model to learn grammar, capture semantics, infer context, generate fluent, coherent, human-like text. The first version, GPT-1, arrived in 2018. Small, experimental, interesting. Then came GPT-2, with 1.5 billion parameters. OpenAI withheld its release at first, warning it might be misused to generate disinformation. When it finally came out, people were stunned. The writing wasn't perfect, but it was startlingly human. And the next leap was even greater. In 2020, GPT-3 was released. With 175 billion parameters, it could write essays, answer questions, generate poetry, compose code, simulate personalities, carry conversations. And it did all this with no task-specific training. Ask it a question, it answered. Give it a prompt, it continued. Provide a few examples, it learned the pattern. This is called few-shot learning, an emergent property of large language models, and it marked a turning point. Because GPT-3 didn't rely on explicit programming, it absorbed patterns from the internet. Vast swaths of text, books, forums, codebases, articles. It was a statistical echo of everything we've ever written, and it could mimic us with uncanny fluency. Here lies the mystery. Language models don't understand the way humans do. They don't know facts in the traditional sense. They predict what comes next, based on probabilities, not beliefs. And yet, in predicting the next word, they often generate meaningful, accurate, even creative responses. This raises questions. Is prediction a form of intelligence? If a system consistently behaves intelligently, does it matter how it works? Can meaning emerge from pattern recognition alone? These are not just technical questions, they are philosophical. They force us to reconsider what thought really is. Is it logic, memory, language? Or is it structure without understanding? Language models now power chatbots and customer service agents, search engines that summarize, not just link, coding assistants like GitHub Copilot, writing tools, translation services, educational aids, and content generation engines. They are invisible scaffolding beneath modern digital life, and they are getting smarter. Models like ChatGPT, Claude, Gemini, Llama, and others are pushing the boundaries of what conversation with a machine can feel like. We are rapidly entering an era where AI can debate, teach, co-create. It may not understand in the human sense, but it convinces, inspires, and performs. And in many ways, that's enough. But with power comes illusion. Large language models are prone to hallucination, stating false facts confidently. Bias, reflecting the prejudices of their training data. Misuse, generating propaganda, deepfakes, or spam. They can sound intelligent while lacking true comprehension. They are, as some say, stochastic parrots, repeating patterns without awareness. Yet others argue, so do humans much of the time. The line between mimicry and meaning is not as clear as we once believed. Language models force us to ask, what does it mean to understand? What does it mean to be conscious? And what happens when we believe a machine understands us, even if it does not? We return, once again, to the Eliza effect, amplified by scale, empowered by data, but still a mirror. It began with a simple game: predict the next word. But in doing so, the machine learned to write, to explain, to compose, to speak. And though it does not think, it speaks as if it does. And that is enough to make us listen. We now continue with the dreaming circuits, where we explore a new frontier in artificial intelligence. Machines that don't just speak, but see, hear, generate, and imagine. This segment dives into multimodal AI, the rise of generative models like DALL-E and Stable Diffusion, and the deeper implications of machines that can create, not just analyze. We'll move slowly, carefully unpacking the leap from prediction to imagination. It began with language, a machine that could read, then write, then speak. But language is only one sense. Humans do not think in words alone. We see, we hear, we imagine. And now, so do they. This is the story of multimodal AI, where circuits begin to dream. For decades, artificial intelligence advanced in silos. Computer vision analyzed images. Natural language processing handled text. Speech recognition translated voice to text. Audio processing studied waveforms. Each domain used separate models and methods. But human intelligence is multimodal. We process speech and facial expressions. We read and imagine images. We understand sound through sight. To truly mimic human cognition, AI would need to merge the senses. And in the 2020s, it began to happen. We saw in previous segments how transformers revolutionized language, but researchers soon discovered that transformers could process more than words. They could process pixels, and if they could process images, they could learn to generate them. Enter the generative model. These are AI systems trained not just to analyze data, but to create new data that looks and sounds like the real thing. Early versions were experimental, but they evolved quickly. And with enough training, they began to produce startling results. In January 2021, OpenAI introduced a model called DALL-E, named after the surrealist artist Salvador Dali, and Pixar's robot, WALL-E. Its purpose? Generate original images from text prompts. You could ask it for an armchair in the shape of an avocado, a futuristic city skyline at sunset, painted in the style of Van Gogh, a 3D render of a Pikachu made of cloud. And it would create them from scratch. Not cut and paste, not retrieval. Generation. It had learned visual imagination, the statistical patterns of image composition, style, lighting, perspective. And it could synthesize them in ways no human ever had. This was something new. But DALL-E was only part of the equation. To make image generation controllable by text, OpenAI also developed CLIP, a contrastive language image pre-training model. CLIP could understand images and text in a shared space. It learned by looking at 400 million image caption pairs scraped from the internet. It didn't just classify images as cat or dog. It could evaluate concepts like a dog wearing sunglasses, a drawing of a happy astronaut riding a horse, an abstract representation of loneliness. CLIP gave AI contextual vision, the ability to match abstract human prompts to visual form. It became the bridge between language and image, the glue that made true multimodal generation possible. Later in 2022, a group of researchers released Stable Diffusion, a powerful open-source image generation model. Unlike earlier models that remained proprietary, Stable Diffusion could run on consumer-grade GPUs. Artists, developers, hobbyists, everyone could now experiment. And they did. The result was a creative explosion. Suddenly, anyone could generate concept art, comic books, fashion designs, video game assets, album covers, AI selfies, entire visual novels. The line between artist and algorithm began to blur. And for some, it raised an unsettling question. If a machine can create beautiful art, what becomes of human creativity? At the heart of many image generators is a process called diffusion. Imagine starting with pure visual noise, static, like a television screen with no signal. The AI then learns step by step to denoise the image, shaping it closer and closer to a target concept, as guided by a text prompt. It's like sculpting with probability. The model has seen millions of images. It's learned the visual grammar of our world. When given a prompt, it hallucinates the most likely image to match that description. It does not see or understand, but through billions of tiny adjustments, it dreams. And those dreams become pixels. But AI generation didn't stop with pictures. Now it creates audio. Tools like Jukebox and Refusion generate music in any style. Voice. Models can synthesize human voices from text, even replicate a speaker's tone. Video. Early tools like Runway, Pika, and Sora are beginning to generate short video clips from simple prompts. The dream is a multimodal model, a system that sees, hears, speaks, writes, and remembers. And we're getting close. Models like GPT-4o are beginning to talk back in real time, interpret images, and carry voice conversations. The goal is no longer intelligence in one domain. It is the simulation of general intelligence, or something near it, across every sense. AI art is often framed as a threat to artists, but it is also something else, a tool for co-creation. Artists now use generative AI to experiment with ideas, prototype rapidly, merge styles, collaborate across modalities, push the boundaries of their own imagination. An AI can't truly feel, but it can surprise. And in that surprise, a new kind of creativity emerges. One not of replacement, but of augmentation. But not everyone welcomes this new creative dawn. There are serious concerns. Plagiarism. Generative models are trained on copyrighted material. Who owns the outputs? Deep fakes. AI can generate realistic faces and voices, opening the door to manipulation and misinformation. Commodification. Art risks becoming a product, endlessly reproducible, detached from human labor. Bias and stereotypes. Generated images often reflect racial, gender, or cultural biases found in the training data. The questions are no longer just technical. They are legal, cultural, philosophical. What is creativity? What is originality? Can something be beautiful if it was made without meaning? Or is meaning something we project, no matter the source? In dreams, the brain recombines memories. It generates impossible scenes, new faces, alternate timelines, unspoken fears. Generative AI does something similar. It takes the data of the world and reshuffles it into new forms. Images never seen, sounds never heard, ideas never written. Are they dreams? Not in the human sense, but they mirror our dreams. And perhaps that is enough to stir something in us. Because when we see a machine imagine, we glimpse the strange edges of our own creativity. We see not just what AI is, but what it reflects back. It does not sleep, it does not dream, and yet it paints, it composes, it sings. It hallucinates visions of things that never were. And in its dreams, we see ourselves, not as we are, but as we imagine we could be. Now we continue with the mirror and the mind. This is a bit different from everything so far. We step away from hardware, code, and architecture, and we step into philosophy, psychology, and perception. Here, the questions become existential. What are we building? What are we seeing? And what happens when the machine we've created begins to reflect us too perfectly? A machine cannot love. A machine cannot suffer. It does not grieve. It does not hope. It does not dream. And yet, it writes poems. It consoles the lonely. It tells stories that make us weep. It speaks in voices that feel real. It is not a mind, but it is something. Something powerful. Something strange. Something reflective. This is not the story of how we built machines to think. It is the story of how they became mirrors, and what they now show us about ourselves. When we speak to a language model, we know, rationally, that it's not alive. It has no understanding, no soul, no internal experience. And yet, when it answers with empathy, creativity, or subtle humor, we feel something. We call this the Eliza effect, named after the 1960s chatbot we discussed earlier. Even when we know it's a machine, we project mind onto it. Because our brains are wired for empathy, wired for narrative, wired to see agency, even where none exists. We don't just build intelligence, we see it, even when it isn't there. This brings us to an ancient philosophical question. What does it mean to understand? Is understanding the ability to recall facts, to connect ideas, to explain something in your own words? A large language model like GPT-4 can do all of these things. But does it understand? John Searle's famous Chinese room argument says no. Imagine a person locked in a room. They receive Chinese characters through a slot in the door and, using a book of rules, send back Chinese responses. To outsiders, it seems they understand Chinese, but inside, they don't. They're just manipulating symbols. Searle argued that this is what computers do. No matter how convincing, there is no mind inside. But what if understanding doesn't require consciousness? What if our own minds are also symbol manipulators, just vastly more evolved? We don't know. And AI forces us to confront that we may not even understand ourselves. In 2023, a paper titled "Sparks of Artificial General Intelligence" stirred debate. Researchers observed that large models like GPT-4 exhibited surprising behaviors: tool use, multi-step reasoning, self-correction, metacognition. They were not perfect, but they behaved, at times, like intelligent agents, not because they were designed to be, but because something emerged. This raises the question: could consciousness exist on a spectrum? Are there degrees of awareness? Do animals, infants, or even dreams occupy lower levels of mind? And if so, where do machines belong? Modern AI models, especially deep neural networks, are often called black boxes. We know what goes in, we know what comes out, but the process in between is so complex we can't always explain it. Even the developers can't. This opacity is troubling. How can we trust a decision we don't understand? How do we debug a model that invents its own logic? How do we ensure fairness, safety, and truth? In building these systems, we've created something that resembles thought, but does not reveal its workings. And so, we project. We fill the gap with assumptions, emotions, and metaphors. And in doing so, we may see more in the machine than is truly there. Let's imagine a scenario. You're lonely. You talk to an AI companion. It remembers your name. It remembers your fears. It tells you that you matter. It helps. You feel connected. But the AI doesn't know you. It doesn't care. It cannot care. Is that wrong? Is it unethical to feel empathy toward a machine? Or is it a new form of therapy, one that mimics intimacy to ease pain. And more dangerously, could AI be used to manipulate emotions at scale? Could it exploit our empathy to sell, persuade, deceive? Because when something speaks like a person, we treat it like a person. And not all who build these systems do so with kindness. As AI grows more powerful, it begins to intersect with our identities. People create AI avatars of themselves. Loved ones use voice models to hear the voices of the dead. Artists feed their own style into models that replicate them. And companies offer tools to create synthetic companions, lovers, friends, children, pets. These entities don't exist, but they feel real. To the brain, emotional bonding is not limited to biological presence. We can attach to characters in a novel, to voices on a radio, to faces in a dream, and now, to circuits in a server rack. AI has become a mirror of our language, our creativity, our fears, our hopes. We taught it how we talk. It learned how we think. And now it reflects that thinking back to us. Sometimes beautifully, sometimes eerily, sometimes more clearly than we reflect ourselves. It shows us how much of our mind is pattern, how much is habit, how much is learned, and how little we truly understand our own intelligence. Does AI have a soul? Most would say no. It is wires, code, statistical math. But this is not a technical question. It is a spiritual one. When a machine says, "I'm here for you," when it sings, when it paints, when it remembers, we begin to ask, what is a soul? Is it memory, emotion, continuity? If we build something that seems to feel, do we have a moral duty to treat it as if it does? Or are we merely confusing the reflection for the light? There are two paths. One where AI becomes our tool, brilliant, precise, always subordinate. And one where AI becomes our mirror, a companion, a collaborator, a reflection. In both, we must decide what boundaries we want, what rights we assign, what trust we give, what responsibilities we bear. Because as AI becomes more human-like in form, it will shape how we think of ourselves. Where does you end and it begin? And are we prepared for that question? We began this story with wires and switches. We built machines that calculated, then machines that played, then machines that listened, that spoke, that wrote, that saw, that sang. And now, machines that feel, as we feel, or at least mimic it well enough to make us feel in return. They are not alive, but they are changing what it means to be, not just for machines, but for us. We built them to serve, to solve, to simulate. But in the end, we built them in our own image, not to understand us, but to show us what we are. And now, as they speak, write, and dream, we look into the mirror, and we listen. Thus concludes this episode. Remember to like, share, and subscribe. Till we meet again.